Dear students, today we shall go through yet another lecture on shear strength of soils. This is the second lecture in a series of 5 or 6 lectures which I plan to give. If you remember right, in the first lecture I gave you an idea about what shear strength is all about, why we need to study that. As usual, let us first go through a quick review of what we already know before we go on to learn something more. So, let me start with the first slide of today's lecture, which is actually a review of what we had seen last time. Take this slide for example. In the last lecture, we had a brief overview of several aspects, such as what is the importance or significance of shear strength. In order to understand what shear strength is, what shear stresses are, we need to calculate the stress at any point on any plane. This aspect was emphasized in the last lecture, and in order to do this computation of stresses at any point on any plane, we also briefly looked into a concept known as the concept of Mohr circle. We shall see a little more of that today. Then I also just gave you an idea as to what kind of theories are available in order to see whether a soil will remain stable, will fail under the action of shear or not. In order to know what is this shear strength of a soil, we need to have methods to measure them, not only in the lab, but also if possible directly in the field. So, we also had a look at what kind of methods are available for this purpose. This was what we covered in the last lecture. A little more detail of what we saw in the last lecture is given in the next few slides. So, what is significance of shear strength for example? It is necessary primarily for the design of geotechnical structures against shear failure. What are the geotechnical structures? There can be many examples. For example, foundations, excavation. Even an excavation is rightly called as a geotechnical structure because it is made in earth. Embankments, slopes, retaining walls and any number of other earth structures, they all come under the category of geotechnical structures, and they are likely to fail if the shear stress along any plane at any point exceeds what the strength of the soil against shear is. So, and that is why the significance of learning shear strength. Okay. In order to know how to compute shear stress at any point, so that we will know whether that stress is below or lower than the strength of the soil against shear, we need to have the method to compute the stresses at a point on any plane. So, in order to check for shear failure, it is necessary to have a method to determine the shear stress along any plane at any point in a soil mass. For example, suppose I take a point P in an infinite soil mass. There can be any number of planes passing through that point P, actually infinite number of planes. Take any plane CA and an element at the point P, a so called parallelepiped. In 2 dimensions it becomes just a rectangle. Let the angle that CA makes with the horizontal be theta. Now, this element can be exaggerated for visualization and represented as shown here in this key diagram. You see here, this small element is expanded into a set of 3 planes. Actually, all the 3 planes pass through this point P, but for convenience we take them like this, and in the limit, when the dimensions of these planes reduce to or tend to 0, the element itself will tend to be a point here. So, take these 3 planes AB, BC, CA. In general, on any plane there will be stresses which can always be resolved into normal and shear components. So, the normal component on this plane is sigma y, shear stress is tau x, on the other plane sigma x and tau xy. Now, the notation used here follows a certain sign convention. For normal stresses, compressive positive, tensile negative is chosen. So, here a compressive normal stress sigma y acts on the plane AB. The normal to the plane AB is in the direction y, and according to the chosen coordinate axis, and so the stress is called sigma y. So, also sigma x. Tau xy or tau ix, they represent shear stresses according to the sign convention along the positive axis on a plane with negative outward normal, the shear stress is positive. For example, take plane AB, the positive axis is in this direction and it is on a plane with a negative outward normal. The negative outward normal of plane AB is in the negative y direction, and therefore, a positive shear stress acts in the positive direction of this plane. That is why tau ix in the direction x is taken as the positive shear stress. So, also tau xy. Now, with this we will be in a position to calculate the stress on any arbitrary plane CA, provided we know the stresses on AB and BC. So, stresses on AB and BC are supposed to be known, and usually they are known because, for example, take the plane AB, that is horizontal. The stress there is essentially due to the weight of the column of soil above it, and the stress on the vertical plane is a fraction of that, depending upon what is known as the coefficient of lateral earth pressure, about which you must have definitely studied in some other lecture. Okay. If we have this scheme of stresses on a set of planes, in terms of the stresses on AB and BC, we can express the stress on CA from a very simple consideration that this element and therefore, that point P must be in equilibrium. Now, suppose the length of AC is capital L, correspondingly BC will be L sin theta, AB will be L cos theta, and therefore, we will be in a position to calculate the total forces on each one of these planes and find out what is the condition required for satisfying equilibrium of these forces. Force on AB, for example, can be calculated as sigma y into L cos theta. Force on BC can be calculated, for example, as tau xy into L sin theta. The force on AC will be sigma into L and tau into L. In order for equilibrium to be maintained on this plane, either parallel to it or perpendicular to it, we can show by resolving the forces that the stress sigma must satisfy the condition that sigma is equal to this and stress tau must be equal to this. This is what we discussed in some detail in the earlier lecture. So, for the purposes of this lecture, today's lecture, we will take for granted that by resolving and satisfying equilibrium, we will be able to get these two stress values. So, all the terms on the right hand side are known, and therefore, it is possible to calculate the unknown stresses sigma and tau, particularly tau, which is what we are interested in, because that is the shear stress on any plane on CA. If the shear stress exceeds the strength along this plane, then shear failure will take place. Now, in order to compute these stresses, there is also a geometrical method available, which is based on a concept known as the Mohr's circle concept. This is a circle which is so ingeniously devised that if you plot the known stresses and follow certain geometrical procedure, you can calculate the unknown stress sigma and tau on any arbitrarily inclined plane CA. Let us take a look at this key diagram once again, which you are already familiar with, AB, BC, CA, and the stresses are sigma x, sigma y, tau xy, sigma and L. Now, let us see the geometrical procedure which is used for computing sigma and tau on the plane CA. First, we choose a set of axes, one axis for all the normal stresses, another axis for all the shear stresses. We plot the normal stress sigma x here as shown, point J, sigma y, that is point K. Then we draw a so called Mohr's circle, whose center will be at the midpoint between sigma x and sigma y, and whose radius will be given by sigma y minus sigma x by 2 whole square plus tau xy by 2 whole square. Now, with this radius, if you draw a circle, then this height obviously will be given by tau xy, and a point L will have coordinates sigma x tau xy, correspondingly a point M will have sigma y tau x, and the center will be having a coordinate sigma x plus sigma y by 2. In addition, it can be shown that point B will have the maximum possible normal stress, which is called as the major principal stress sigma 1, and point D will represent the minimum possible normal stress, that is the minimum principal stress sigma 3, and any point C as shown here, having stresses sigma and tau will represent the stresses on the plane CA. Since CA is at an angle theta with respect to the horizontal, on this drawing if we plot a plane EC at an angle 2 theta with respect to this line joining L and M whose coordinates are sigma x tau x y and sigma y tau y x, then we get the point C whose coordinates are sigma tau. There is also another method of obtaining the value of C through drawing lines MP and PC, which we shall see in a subsequent slide. So, this is what is known as the general Mohr circle, which helps us to compute the normal and shear stress on any arbitrary plane, provided we know stresses on any two perpendicular planes passing through the same point and the angle theta. Now, having a method to compute C, next step is to know whether failure will take place along any particular plane, and for this we have several failure theories. An idea about these failure theories I had given in my earlier lecture. In today's lecture, we shall try to see a little more about these theories. For all practical applications, suffice it to say that a linear relationship between stress and strength is sufficient to determine whether failure takes place or not. This is what is known as the Mohr-Coulomb failure plane. On the Mohr circle, this can be expressed by a line having an equation S is equal to C plus sigma tan phi, as we shall be seeing a little later. There are many methods to determine this shear strength. Direct shear test is one of them. This is a typically laboratory test, although there are also large scale direct shear tests meant for field applications. Then we have triaxial shear tests, which is an improved variation of this shear test called the direct shear test. Then we have certain quick tests which can be conducted both in the laboratory and in the field, a little less rigorous than the first two tests, and they are also very useful, and they are known as the unconfined compressive strength test UCS or UCC and the vane shear test VST. In a nutshell, what we have seen so far is that there is a method, or there needs to be developed a method to compute normal and shear stresses on any arbitrary plane, and it is also necessary to have a failure criterion or a strength theory to know whether failure will take place along any arbitrary plane or not. And then we need to know what the strength is in order to assess whether failure will take place, and for that we have methods. And then in order to compute the stress, finally we have a nice method, geometry based method known as the Mohr circle. Incidentally, the Mohr circle itself is based on certain equations which we had developed rigorously, and therefore either we can use the geometrical technique or directly the equations. We will see a few examples a little later, and there both the concepts will be used to show that certain quantities which are associated with shear strength determination can be computed either from Mohr circle or by direct equations. In today's lecture, what we shall do is to take a closer look at this Mohr circle, how it is constructed, different variations of this Mohr circle for different conditions, and also a couple of examples to see how Mohr circle can be applied to compute certain parameters which are associated with shear failure. So, first a review of the Mohr circle concepts. What is Mohr circle meant for? It is meant for determination of normal and shear stresses on any arbitrary plane at an angle theta to the x axis, and it makes use of the geometrical concept of the circle. Let us see how a Mohr circle is constructed for a general set of stresses. What is meant by a general scheme or general system of stresses? Take a look at this familiar key diagram which is on the right. This shows, as we have already seen, three planes passing through a point, but slightly exaggerated to indicate an element in equilibrium. This set of stresses shown here is what I am referring to as the general set of stresses or general scheme of stresses. In the general case, we have a normal and shear stress on each one of these planes. Now, how do we construct a Mohr circle, and what do we construct it for? We are constructing the Mohr circle to determine sigma and tau on a plane AC in terms of sigma x, sigma y, tau x y and the angle theta. So, how does this go? Step by step, let us see. The first step is to choose an x axis for normal stresses. All these normal stresses sigma, sigma y, sigma x, they will be plotted along the x axis. Then we choose an origin O, and then an y axis meant for shear stresses. Having chosen the set of axes, now we choose the center of the Mohr circle. For that, we start with plotting the known stresses. Take sigma x for example. Find out the point J whose x coordinate will be sigma x. Sigma x is a known normal stress. Then at J, plot the shear stress tau x y, which is also known. Then you get the point L. Similarly, plot sigma y and get the point K and the point M whose coordinates will be sigma y tau x. So, now we have two extremities L and K of a typical diameter of the Mohr circle LK. Now, that intersects the x axis at point E, and obviously E is the center of the circle which will pass through both L and K. So, now construct that circle. This is the circle. This circle intersects the x axis at points D and B. They have a significance, as I briefly mentioned in 2-3 slides ago. Point D has the least possible normal stress here, and that is known as sigma 3. We now see here the radius of the Mohr circle, which we plotted with E as the center and EL as the radius. The magnitude of this radius is sigma y minus sigma x by 2 whole square plus tau x y whole square raised to the power of half. The point D will have a coordinate sigma 3, which can be either calculated or measured from the Mohr circle. Similarly, the point B will have coordinates sigma 1, which can be measured or computed, and this completes the Mohr circle for a general stress of stress. Now, if we want the stress on a plane like CA, all that we need to do is to know the angle theta, and then from this reference diameter draw a line at an angle 2 theta taken in the anti-clockwise direction, and this red line typically represents the plane which we will get corresponding to the point C, whose coordinates will be sigma and tau. So, point C represents the stress levels on the plane AC. Okay. Now, it is also possible to compute these stresses by these equations, as we have seen earlier. If we compute them from the Mohr circle or measure them off from the Mohr circle as the coordinate of the point C, the horizontal coordinate and the vertical coordinate, we will get the same values of C, sigma and tau as from the numerical computation. So, these expressions will be obtained also from the Mohr circle, and these are what are the stresses which are unknown on the plane AC. In addition, now as we have seen, there are 2 points D and B which have the minimum and the maximum stresses. How to compute these stresses? We can of course measure them off from the Mohr circle, which is plotted to scale, but we can also compute them. For computing these, we use this simple notion that sigma 3 is the minimum possible stress, sigma 1 is the maximum possible normal stress, and we already know what sigma is. We have an expression for sigma. This is the expression for sigma, and if sigma has to be minimum or maximum, it simply means mathematically that d sigma by d theta must be 0. So, take d sigma by d theta, put it equal to 0, and this is the condition that you get. Now, under what conditions sigma this expression becomes 0? This expression becomes 0, as you can verify easily, when theta is equal to tan inverse of sigma x minus sigma y by 2 tau x y. When theta is equal to this, 2 theta will be equal to tan inverse of sigma x minus sigma y by tau x y, and cos 2 theta can be correspondingly computed, sin 2 theta can be correspondingly computed, and then you substitute in this equation, you will find that this equation is satisfied. If that is the case, then for this value of theta, corresponding to this value of theta, what will be the maximum value of sigma and the minimum value of sigma, which will correspond to d sigma by d theta equal to 0. Both of them can be computed, and it can be shown that sigma maximum is sigma 1 equal to this, sigma minimum is this equal to all this prime quantity which is on the right within the brackets. Now, how do we get two equations corresponding to theta? What happens is, when tan theta is equal to this, it is possible to get this expression satisfied both when sin 2 theta and cos 2 theta are positive, and also when sin 2 theta and cos 2 theta are both negative. When sin 2 theta and cos 2 theta are both positive, this equation is satisfied, and the corresponding sigma value we get from this expression will be equal to sigma 1. On the other hand, when sin 2 theta and cos 2 theta are both negative and this expression is satisfied, then this becomes 0, and the corresponding sigma becomes the minimum value sigma 3, which is given by this expression. So, it is possible to calculate the minimum and maximum by a simple differentiation and substitution of the condition under which the stress becomes minimum or maximum. Now, let us see once again the construction of a Mohr cycle, but this time for a specific case where the principal stresses are known, or rather the principal planes are known. Take the key diagram once again. This key diagram is similar to the earlier one, but the only difference is here the horizontal planes AB only has a normal stress now. The shear stress is 0 on this because AB is a principal plane. Let us take sigma y to be greater than sigma x, and then sigma y becomes the major principal stress. So, this is equal to sigma 1. On the other hand, BC automatically becomes sigma x, or the minor principal stress acting horizontally on the plane BC, and correspondingly, if you take a plane CA at an angle theta with respect to the horizontal or major principal stress, then the normal and shear stresses on this plane AC, sigma and tau, can now be computed in terms of sigma 1 and sigma 3, either by Mohr cycle or from the rigorous expressions. Let us see the construction of a Mohr cycle when the principal stresses are known. As before, take the x axis, that is normal stress axis, take the origin O, then plot the y axis for shear stresses at right angles to the normal stress axis, choose the point D. Earlier D was not known, but now we know D because the value of sigma 3, the minor principal stress, is known. Then choose the major principal stress as the x axis and get the point B. Obviously, the center has to lie between D and B at its midpoint. So, choose the origin E at the midpoint of the length dB. It will be equal to sigma 1 plus sigma 3 by 2. Plot the Mohr circle with the radius as sigma 1 minus sigma 3 by 2. Then take an angle 2 theta with respect to the horizontal, now that is the line EB. Get the red line, the coordinates of the point where the red line intersects the Mohr circle will be nothing but sigma and tau. So, point C will represent the stress state on any arbitrary plane AC at an angle theta, and it can be shown that sigma will be equal to this, tau will be equal to sigma 1 minus sigma 3 sin 2 theta. Now, once we know these two expressions, we can compute sigma and tau from knowing the angle theta. So, looking at this slide, we can see that there is a minor difference between general set of stresses and principal stresses. The difference is that when there are principal stresses acting on the known planes, there are no shear stresses, and to that extent the plotting of the Mohr circle becomes a little easier, and computation of the stresses on the plane AC also becomes a little easier. Now, do we really need a geometrical method for determining the stresses? Can we not do with just the, since we know all the parameters on the right hand side, we can always compute the stresses sigma and tau. Then where do these geometrical methods score? The advantage of a geometrical method, as you will see a little later again, is that it gives you a very nice concept or ability to visualize how the stresses vary over the planes. A geometrical concept is always easy to visualize and comprehend than an equation, and that is the reason why we have gone to such great length as to understand how a Mohr circle is plotted. It helps to visualize how the planes are oriented, how the stresses are varying from plane to plane, and which is the plane which is critical and why. So, let us see further a method known as the pole method, which is also used for plotting the Mohr circle. This is called a pole method because of a specific point on the Mohr circle which is known as the pole. For example, to locate a pole, you draw a line from a known point on the Mohr circle parallel to the plane on which the state of stress represented by that point acts. What I mean is, you have a Mohr circle, you know the state of stress on a particular plane, choose the point on the Mohr circle which represents this state of stress, and there draw a line parallel to the plane whose state of stress that point represents. Then the point of intersection of this parallel line with the Mohr circle is called the pole. It is also sometimes referred to as the origin of planes. The reason why we see this is very simple. If you see the previous slide, the point C was located by taking an angle 2 theta, measuring off an angle 2 theta with respect to the normal stress axis in the anticlockwise direction, because the plane CA made an angle theta with respect to the horizontal axis. Rather than going by this concept, we can also proceed by simply knowing the orientations of the planes. That is what the pole method is all about. Start once again with this index or key diagram for general stresses. So, now if we have general stresses, how do we use the pole method for determining the stresses sigma and tau? We follow a series of steps as always, as we have been doing in the earlier instances. First, draw the normal stress axis, choose the origin and plot the vertical axis, plot sigma x, find out the points j and l, plot sigma y, find the points k and m, join LM, get E, draw a Mohr circle, get the points D and B. The radius will be given by this expression. Midpoint E will have coordinates sigma x plus sigma y by 2. D will be equal to sigma 3, B will be representing sigma 1, and now comes the determination of the point C on the Mohr circle, which will correspond to the state of stress sigma tau. For this, rather than plotting a line at an angle 2 theta as we did in the previous instance, we will now choose the point M and draw a line MP. Why do we choose point M? Because point M on the Mohr circle is a point whose stress coordinates are sigma y tau ix. That is nothing but the set of stresses normal and shear acting on the plane AB, which is horizontal. So, point M represents the state of stress acting on a plane AB, which is horizontal. So, from point M, if you draw a line MP parallel to the plane on which this state of stress acts, then the point P where it intersects the Mohr circle is known as the pole. The property of the pole is any line that you draw through the point P, the pole, will have a corresponding point of intersection on the Mohr circle, and that point of intersection will have coordinates representing stresses which will be acting on the plane passing through the point P. So, for example, In order to know the stress on the plane AC, from the pole draw a line which represents the plane CA, that is, draw PC parallel to CA. Obviously, then C, which is the point of intersection of this red line with the Mohr's circle, will have the state of stress given by the plane parallel to PC, that is plane CA. Then it can also be easily shown that plotting an angle 2 theta from here and joining E with C will also give you the same point C as the red line drawn from the point P. So, this is an alternative method, the so called pole method, for determining the point C. It can be also applied to a situation where we do not know the general state of stress, but we are fortunate enough to know the normal and shear tangential stresses on the planes AB, BA, BC and CA. The value of sigma and the value of tau are to be determined in terms of sigma 1 and sigma 3. The plotting of the Mohr circle does not require any explanation. We can just watch the progression of steps. We have so far plotted the minor principal stress and major principal stress. We have chosen the center of the potential Mohr circle. We have got the Mohr circle and its radius. We got the point C, and how we have obtained is by choosing the point B, which represents the state of stress corresponding to sigma 3. That means the plane BC will have to be a line which is horizontal passing through the point B. So, from point B, if you plot a line which is parallel to the plane AB on which this stress sigma 1 acts, then the point P becomes the pole, and PC at an angle theta will give you sigma tau, and PC is plotted parallel to CA. Or alternately, plot 2 theta with respect to the line DB and get the point C. There is also a possibility that the line AB or the plane AB is not horizontal. We have been assuming that the two known planes are horizontal and vertical, but that is only a special case. In the most general case, the line AB representing the major principal plane could be an inclined plane. The line BC representing the minor principal plane could be a plane which is at right angles to AB and also therefore inclined to the vertical. In such a case, if you have a plane AC inclined at an angle theta to AB, we can follow the same Mohr circle concept and get the stresses on the plane AC. The difference will be that from the point B now, rather than drawing a line horizontally to represent the plane on which stress is sigma 1, now we will draw a line BA which is parallel to the known direction of BA on which sigma 1 is acting, and where it ends, that is the point B, P. And from P, if you draw a line PC at an angle theta that is parallel to AC, then you get sigma tau. Sigma will be now equal to O to this point and tau will be from here to C. And this also is possible to obtain by plotting a line 2 theta through this point E with respect to the horizontal. The corresponding expressions for sigma and tau, which we have already seen, will be satisfied by this point C. Now, having had an exposure to the method of determining the stresses on any plane, let us see what is this concept of failure, which will help us to assess whether under given circumstances of shear stress and shear strength, failure can take place along a plane in a soil. So, what is this concept of failure? Let us go back to physics and try to understand failure along a plane of contact between two bodies which are experiencing friction at the plane of contact. Let us say there is a block here, rectangular block resting on a plane offering friction. This rectangular block, let us say, has a weight W. Corresponding to W, there will be a normal reaction N. Now, suppose you apply a shear force T, a tangential force T, shown by this green line. Because there is friction between the bodies, a force F in the opposite direction will be automatically mobilized, and that will resist T, and for equilibrium T will be equal to F, N will be equal to W, or in other words the resultant R will be equal to the resultant P. The angle which R makes with the vertical will be the angle which P makes with the vertical, that is alpha. This is a situation when the block is in equilibrium, but let us increase the value of T until the block reaches the state of so called incipient slippage, that is T has now achieved its limiting value. Corresponding to this angle alpha has reached its maximum possible value. Under these circumstances, the normal stress S, or the normal force N, I am sorry, will balance the force W, and F, which is now going to have its limiting magnitude, will once again be opposing capital T and be equal to capital T, and the angle which the resultant makes with the vertical now will be the maximum possible angle value of this angle alpha, and that is referred to as phi. Then this alpha is known as the angle of obliquity, and this serves as a condition representing failure. What is this angle alpha equal to? It is equal to tan inverse of the angle phi, because alpha and phi are both equal. What is the tan inverse of angle phi? Is nothing but F upon N, and therefore, we have alpha equal to tan inverse of tau upon sigma, because the area over which F and N act is the area of the plane of contact here, and that remains the same. So, if that plane has a magnitude A for area, then shear stress on this contact plane is F limiting upon the area, normal stress on the contact plane is N by area of contact, and therefore, alpha is tan inverse of tau upon sigma, or phi is tan inverse of tau upon sigma. Whereas, this expression is valid for all values of alpha. When it is equal to phi, it becomes valid for the limiting state, and this is what is known as the state corresponding to limit equilibrium, and it is only possible to know the shear stress tau at this particular state, because we know that even a slight increase in tau will cause shear failure here at the plane of contact, whereas at any other value of tau less than the limiting value, we only know that equilibrium exists, we do not know really what fraction of tau has been really mobilized. Having decided what criterion is satisfied during failure, that is, having known that for failure alpha has to be maximum or tan inverse of tau by sigma has to be maximum, we can now define failure in terms of the Mohr circle concept also. For example, it is very obvious that failure takes place when tau upon sigma is maximum, because tau upon sigma represents tan of the maximum angle of obliquity, that is phi. So, we incidentally also have a criterion which is obvious from here, that is tan phi, tan of the angle of obliquity with its maximum value is equal to tau upon sigma. So, tan of phi equal to tau upon sigma, or sigma equal to, or rather tau equal to sigma tan phi becomes the criterion defining failure. Go to Mohr circle, find out at what point sigma becomes equal to tan phi. I am sorry, tau becomes equal to sigma tan phi. Plot the normal stress, choose the origin, plot the vertical or shear stress, choose the point E, which is the center of the Mohr circle. Plot only half the Mohr circle for convenience and clarity with EA as the radius. We know sigma 1 and sigma 3. So, we get the Mohr circle. Sigma is the normal stress at any point on the Mohr circle, and tau is the shear stress at any point on the Mohr circle. And if we want to know what is that point on the Mohr circle which will correspond to the state of stress during failure, what we need to find out is when at which point tau upon sigma becomes maximum, because that will represent the condition sigma equal to rather tau equal to sigma tan phi, which defines failure. So, suppose I choose this pole. We have already seen that this has got to be the pole for a situation where major and minor principal stresses are known and plotted. From the pole, draw a line to a point C, which will represent the point where tau upon sigma will be maximum. Now, we know that tau upon sigma maximum corresponds to tan inverse of the angle phi. So, there exists an angle phi whose tangent is tau upon sigma, and tau upon sigma has its maximum possible value. Such an angle can only be this angle phi, which can be obtained by drawing a tangent through the point C from point O. The tangent of this angle phi is tau upon sigma. Therefore, this angle phi is nothing but the angle of maximum obliquity, which defines failure. So, the plane AC, which has been plotted from the pole up to the point C, is nothing but the plane on which acts the stresses tau and sigma corresponding to failure. So, AC becomes the failure plane. This failure plane AC makes an angle with the horizontal, which we now call as theta critical, because that corresponds to the critical possible angle. What is the value of theta critical at which the plane of failure will lie? Theta critical from simple geometry is obviously equal to half the angle OCA plus phi. So, 45 degrees plus phi by 2. This means that if we know sigma 1, sigma 3 and plot a Mohr circle with E as the center, all that we need to do is go to point A, draw a line AC at an angle theta critical equal to 45 degrees plus phi by 2, and that point C will be representing the state of stress at the time of failure, incipient failure. Now, this means that we need to know the angle phi. This means that we need to have a method to determine the angle phi. There are laboratory techniques to determine this angle phi, as we will be seeing later. Now, how do we say that theta is equal to 45 degrees plus phi by 2 from theoretical considerations? It is very simple. For a given value of sigma 3 and C, the failure will occur when sigma 1 is minimum. Therefore, take the expression for sigma 1, which we are already familiar with, and maximize that. When that is maximized, you will have d by d theta equal to this equal to 0. This, when you simplify, you will get cos 2 theta plus sin 2 theta tan phi is equal to 0. That is nothing but theta equal to 45 plus phi by 2. From this, we can derive further relationships using the Mohr circle. Suppose this is the Mohr circle, where this angle is defined as theta critical equal to 45 degrees plus phi by 2. We can also use the sine and cosine of this angle phi and show that sine of this angle phi is nothing but sigma 1 minus sigma 3 divided by sigma 1 plus sigma 3, that is equal to this. Or from here we can show that sigma 1 by sigma 3 is equal to 1 plus sin phi by 1 minus sin phi. All these different expressions are useful in different contexts to relate the plane of failure and the states of stress sigma 1 and sigma 3. The failure criterion will also now look like this. We know that the failure criterion is shear stress equal to shear strength equal to C plus sigma tan phi. The expression for C plus sigma tan phi and tau will be equal to this from the Mohr cycle which we have just now seen, and this can be simplified into an expression sigma 1 equal to sigma 3 plus all this, in which theta will correspond to 45 degrees plus phi by 2, the angle made by the plane of failure, the critical angle. This means that failure will take place along a plane which makes this critical angle 45 degrees plus phi by 2, provided the known states of stress sigma 1 and sigma 3 and the values of C and phi of the soil satisfy this relationship. The values of C and phi of the soil, which are known as the shear parameters, can be determined from the laboratory. Then, knowing that the plane of failure makes an angle theta equal to 45 degrees plus phi by 2, and knowing sigma 1 and sigma 3, it is possible to check whether failure will take place along a given plane or not. That same expression which we saw in the previous slide can also be rewritten in this form, where we use now a notation n phi known as the flow value to represent tan square 45 plus phi by 2. Let us see a couple of examples now. In the first example, we have normal and shear stresses on two mutually perpendicular planes BC and BA on a soil element are given. These are plotted in a key diagram which appears on the next slide. The stresses sigma x, sigma y, tau xy are therefore known. What is required is determine the major principal stress, the minor principal stress, the normal and shear stresses on the plane CA, which makes an angle of 37 degrees with the horizontal, and for this purpose use the pole method and the Mohr diagram. We have seen already in detail the step by step construction of the Mohr circle. Therefore, we will not go through that again. All that we need to know is we have a system of general stresses here now, where sigma x, sigma y and tau xy are known. So, we plot sigma x, sigma y, get the points j and k, points L and M, plot the Mohr circle and obtain the point M corresponding to the state of stress on the plane AB. Once we know that, since plane AB is horizontal, draw the line MP horizontally and determine the pole P. Once you know the pole P, you can determine the point C, whose coordinates are C tau, sigma tau. Once you know this point C corresponding to this state of stress, we can easily find out the values of normal stress and shear stress on these planes. Whatever is known is plotted first. So, normal stress on plane BA is plotted as 140, normal stress on plane BC is plotted as 60, shear stress on plane BA and BC are plotted as minus 20 and plus 20 to get the Mohr circle which was shown on the previous slide. From the coordinates of the points B and D, which correspond to major and minor principal stresses, we can measure off these values. We can also use the pole to get the point C and measure off the values sigma and tau from the Mohr diagram. If we calculate it rigorously from the formulae also, we will get the same stresses. The next example is one in which sigma 1 and sigma 3 are now known. So, this is instead of a state of general stresses, this is a state of specific set known stresses. Again, using the Mohr circle and the pole method, determine first the pole, then the major and minor principal planes, the maximum shear stress and the failure plane and the stresses on the failure plane. Under two conditions: one, when sigma 1 plane, that is the major principal plane is vertical and the minor principal plane is horizontal, and case B, when the major principal plane is horizontal. The solution is very simple. As before, plot the Mohr circle and also after determining the pole P corresponding to the principal stress sigma 1, get the failure plane corresponding to the point C and get the stresses. Tau max can be measured off as the ordinate of the point L, that will come to 70. From the coordinates of the point C obtained from the pole method, sigma and tau can be calculated as 92 and 58 respectively. or from rigorous computations we can get tau max must be equal to sigma 1 minus sigma 3 by 2 the radius of the Mohr circle, that is again coming to 70. The angle phi will be sine inverse of the quantities sigma 1 and sigma 3 which are known. Theta is again known from 45 degrees plus phi by 2. We can calculate sigma and tau from these quantities once again by using the same expressions. Thus, it is possible to compute the complete set of stresses either graphically or from rigorous computations. And we will find that all that has happened is the principal planes and the pole have changed positions, and points L and C however remain unchanged, and the maximum shear stress and the coordinates of the point C give rise to the values of tau max and sigma tau. Now, in this lecture we have taken a close look at how to plot a Mohr circle and what it is capable of giving, and we have seen a couple of examples to illustrate these concepts and reinforce these. In the next lecture we shall be seeing the methods of determining the shear strength of a soil, because that is what is going to help us to check whether the stresses which we have so far calculated are going to cause a failure or not. And we will also see a few examples during the next lecture, and this way we will conclude today's lecture by saying that we now have a basis on with the help of which we can check whether a given soil along a given plane is likely to undergo shear failure or not. And this will be useful in many instances such as foundations, retaining walls, etc. Thank you.